Bismillahirrahmanirrahim. Dear students, I'll start lecture number 1 of week number 14, and we'll in this lecture start a new chapter that is about multiple continuous random variables. We have already discussed single continuous random variable, so we'll extend those concepts to more than one continuous random variables. First, I'll take two continuous random variables together and discuss a few topics, and then on we'll try to generalize our expressions to more than two continuous random variables. So the first topic in this chapter is joint cumulative distribution function. Which means joint CDF. As I told you earlier as well many times, when handling discrete random variables, we start with, in general, we start with the probability distributions, and from there we find the CDF. But in continuous cases, we generally start with the CDF and then differentiate that CDF to find the probability distributions, or the PDF. What we mean by a giant CDF, before we move to this concept, first try to understand the concept of giant continuous distributions. If you recall, in a single continuous random variables, the probability of a particular value of that continuous random variable was always 0, and we had strong arguments for that, and we related those arguments and examples to the integration of a particular point. You all know that the integration under a particular point is always equal to 0, and so since the probability is for continuous random variables is in the form of densities, so the probability of a particular point is also equal to 0. So to have meaningful probabilities for continuous random variables, we discussed that we take intervals, meaningful intervals, and then do the integrations on those intervals to find to have those probabilities. This was for a single continuous random variable case. Now imagine there are two continuous random variables. So we'll have the giant CDF and the giant PDF of those random variables taken simultaneously, which means the intersection of the two random variables. And so we'll have intervals on one random variable and the intervals on the other random variables, and when we'll put together, imagine together, we'll imagine them as the areas, the meaningful areas, because we'll have x and y axes and as the two random variables, and so we'll have meaningful areas in terms of probabilities in a 2D plane. So if you understand this, I can move on and discuss the concept of giant CDF. The giant CDF is written as f sub x comma y of x comma y. This is the giant CDF of random variable x, which is continuous in nature, random variable y, which is also continuous in nature, and this is by definition the probability that x is no greater than this, and simultaneously random variable y is no greater than this. You should be able to understand this. So let me give a little pictorial description of this. Suppose this is the x random variable and this is the y random variable. The CDF, the giant CDF of x and y basically says that x is below a particular value x. So suppose this is some small value x, this one. So everything below this uh, is given by this relation. And similarly, we also see that this giant CDF definition also involves that y is below or equal to some value y, and suppose that some value y is here. So everything below this point on y is included in the CDF. So we see that now this gives us all this region. So this all is nothing but the event that x is below this value and y is below this value. So all taken together is basically that the probability of all this will be nothing but the giant PDF. And I hope this is understandable. So I'll move on and discuss a few properties of giant CDF, and these are given in the form of a theorem in your textbook, and that says for any pair of random variables x and y, x and y are continuous. First, the CDF, the giant CDF of x and y obviously has to be 0 and above till 1. So this is basically, if you see this, you move from minus infinity at x and you move from minus infinity at y, and then you keep on increasing the height. Ultimately you reach this point where the total CDF becomes 1. So obviously the range of CDF is from 0 till 1. In B it says that f sub x uh, comma y from minus infinity and y, x from minus infinity at minus infinity and until y, this is equal to f sub x comma y of x comma minus infinity, and this should be equal to 0. And this is obvious because if you imagine this and now see this, so we are saying that the CDF at when x is at minus infinity jointly with y, so whatever the y value of y is, but when you move on to the minus infinity uh, on x-axis, you will reach a region where there will be no intersections, meaningful intersections between x and y. So beyond that, to the minus infinity side, the probability will be 0. And similar is the case with f sub x comma y of x comma minus infinity. So if you move on the y-axis to minus infinity, there will be a point beyond which you will have no meaningful intersections between x and y. So the probability of the intervals beyond that to the minus infinity side, both on x-axis and y-axis, will be equal to 0. And another important point in this theorem is that if we have some point x1 which is greater than or equal to x, and we have some point y1 greater than or equal to y, then obviously the CDF f sub x comma y of x1 comma y1 is greater than or equal to f sub x comma y of x comma y, which means all the higher uh, ranges, areas in CDF uh, are obtained by adding all the previous probabilities. So the plot of this giant CDF is an increasing function So obviously then for all x greater than so all x1 for any x1 greater than x and for any y1 greater than y, the CDF at these higher points should be greater than the CDF at the lower point. So this is simple now, and D, which is obvious, f sub x comma y at infinity comma infinity, which means you reach the infinity, you go to the infinity at x-axis, or you go to the infinity at y-axis, you should reach 1 on the way. So once you reach 1, beyond that there'll be no areas of non-zero probability, uh, areas of non-zero probability, so your CDF will stay at 1. I hope this is clearly understood. I'll move on and solve a quick example. And suppose A and B uh, are two components, some electronic components, and their operating lives are respectively given with random variables x and y. So these are their uh, operating lives. So the operating life of component A is represented by some random variable x, and the operating life of component B is represented by some random variable y. And suppose that their joint cumulative distribution function is given as such: f sub x comma y of x comma y, that is equal to 1 minus e raised to power minus x times 1 minus e raised to power minus y, for obviously x greater than or equal to 0 and y greater than or equal to 0 and 0 otherwise. If that is the case, we need to uh, find the probability uh, that both components have operating lives shorter than or equal to 1 year. Suppose these lives are given in operating lives x and y are given in years. So we need to find that if this is the giant CDF, what is the probability that that both components A and B have lives, operating lives shorter than or equal to 1 year. So the solution is simple. You simply plug in uh, the values here. So this probability is nothing but the probability that x is less than or equal to 1 and y is less than or equal to 1. Now you can also see an indicator of independence here, but you need to think on that. I'll not explain because on that independence concept, because you already know what we mean by independence here. So this is what we need to calculate. So simply plug in x is equal to 1 here, y is equal to 1 here. So you obtain 1 minus e raised to power minus 1 times 1 minus e raised to power minus 1. So that becomes 0.3996. So this is the probability that the operating lives of both the components simultaneously working, operating lives of both the components, joint operating lives of both the components is below or equal to 1 year. So both the components work with probability 0.3996. So we have now completed the initial part about the giant CDF. You know, in continuous cases, we start with the CDF and then differentiate that CDF to arrive at PDF. But since now this is a two-dimensional case, so we should have uh, partial derivatives. So the concept of giant probability density function is easy. You simply differentiate the CDF and you find the PDF, the giant PDF. You differentiate the giant CDF and you find the giant PDF. So the giant PDF f sub x comma y of x comma y is nothing but the derivative of x comma y. But since there are two variables involved, so that will be a partial derivative curly 2 f sub x comma y of curly x curly y. So this is the formula to find the giant PDF. Uh, remember, you need to utilize the partial derivatives here, and you know when you apply partial derivatives on a function of two random variables, you differentiate it variable by variable. So if the function is of x comma y variables, so you differentiate it with respect to x and assume y as constant, and then you differentiate the result with respect to y assuming x as constant, and you obtain the the giant sorry the partial derivative. So this should be simple. There is one theorem that I would like to discuss, and that says that if you want to find the probability that x is within this range and simultaneously y is within this range, and you want to find this probability using the CDF, this is not easy. So my recommendation here, and the recommendation is, if you have to find the probabilities in such rectangular areas, do not use or try not to use the expressions for CDF, because for the expressions of CDF you have to involve 4 CDFs at all the corners of that rectangle, and that means to find this particular PDF, if you want to utilize the expression for CDF, you will place them in this particular order: f sub x comma y, the CDF of x comma y at this x2 comma y2 point, minus the CDF of x comma y at x2 comma y1, minus the CDF of x1 comma y2, and then plus the CDF at x1 comma y1. So you see the plus minus sign and the four corners. I give you the proof as homework. Try to prove that. Even if you cannot, it's not a big deal, but if you can do this, you will have a little more understanding and some extra understanding. So this was just an extra point, that if you have two-dimensional distributions, then to find the meaningful probabilities of certain areas, it is better to utilize integrals than and obviously the PDFs than utilizing the the CDF. A giant PDF has the following properties. A giant PDF has two important properties that I'll now discuss. So a giant PDF, say f sub x comma y of x comma y has the following properties, and these are associated with the axioms, the basic axioms of probability. The first property is that the giant CDF of the two continuous random variables x and y is always greater than or equal to 0, and this is obvious. The probability can never be negative, whether it is giant or a single distribution. And secondly, if you integrate on both x and y axes, the giant PDF of x and y, this should give you 1, which means the total area in terms of probabilities is equal to 1. And if you want to find the probability of certain event A, which is some part of the total distribution, you simply integrate on that particular area the total distribution, and then you obtain the probability of that area. So that should not be difficult. I'll now solve two examples so that you can have some more understanding of the concepts of giant distributions discussed as yet. So my first example now in this chapter. Suppose we have random variables x and y, and they have giant PDF f sub x comma y of x comma y, and say it is C for x between 0 and 3 and y between say 0 and 5, and it is equal to 0 otherwise. So we have a giant distribution of two random variables x and y, and that giant distribution is a constant in this particular range. So it is a kind of giant uniform distribution. Any meaningful area of certain dimension, and the probability of that area is exactly equal to any other area of the same size, same dimension in that distribution. So we need to find first the value of C and probability of certain area A, which is the probability that x greater than or equal to 1 and less than or equal to 3, and y greater than or equal to 2 and less than or equal to 3. So this area between 1 and 3 on x-axis and between 2 and 3 on y-axis is given as event A, and we need to find the probability of that event. So solving this should not be a problem. I'll try to solve it through some plot. So just imagine these two axes. Say this is random variable y, this is random variable x. You see x is between 0 and 3. So if this is 0, 1, 2 and 3, and y is between 0 and 5, so it is 0, 1, 2, 3, 4, and 5. So the statement of the problem says, pardon my drawing, this is simply some line, that all this area is basically the PDF, the giant PDF of the random variables x and y. And what is the value of c? To find c, we know that if we integrate it with respect to x and y, the giant PDF, if we integrate it, we should have probability 1, which means 1 is equal to integral 0 to 3 on x and integral 0 to 5 on y, c times dy dx, and this will ultimately become 15c. So this implies c is equal to 1 by 15, and this should be obvious. Why? Because this is uniformly distributed, and you see, if you divide somehow this area into certain small rectangles or squares, we get 15 squares in total. So the constant c is simply 1 over 15. So there are such 15 c's in the total area. In the second part, we need to find the probability of this event A. So the probability of event A basically is integral 1 to 3, and then from 2 to 3, 1 by 15 dy dx. We can perform the integration, but we, in this particular problem, even don't need to perform the integration, because you see that value of c is 1 by 15, and if this x is from 1 till 3, which means from here till here, and y is from 2 to 3, which means here to here. So this is here y is from 2 to 3, here also y is from 2 to 3, and only these two squares are representing the range on x from 1 to 3. So basically these two rectangles. So simply add the total area. So you see the total area here is 2 by 15. So this is the answer. This is the probability, 2 by 15, for these two rectangles. I'll move on to another example and teach you how to find the giant PDF from a giant CDF. So one more example, and that says that if you have a giant CDF of two random variables x and y, and say it is given as 1 minus e raised to power minus x times 1 minus e raised to power minus y for x greater than or equal to 0 and y greater than or equal to 0, and it is equal to 0 otherwise. We need to find the giant PDF of these two random variables. Solution is very simple. You know, the giant PDF is obtained by applying curly 2 on CDF sub x comma y of x comma y over curly x curly y. So how can we do this? This is so simple. You simply take curly by curly x, and the rest is curly f over curly y, some function which is basically this function. I have written it in another form. So you first take the giant CDF and take the partial derivative with respect to y, assuming x is constant, and then you'll have some expression, and you differentiate that expression with respect to x again, assuming y as constant. And if you perform this, and that is your homework, it is very simple, you will reach e raised to power minus x times e raised to power minus y. You simply need to perform this partial differentiation. Should not be a big deal for you. So for arriving at the giant PDF, you differentiate the giant CDF. One more important and important but yet simple, because we have discussed it many times, a concept, and that is marginal probability density function. Marginal PDF means if you have a giant PDF available, say of random variables x and y, what is the PDF of x and what is the PDF of y, the individual single random variables PDFs. So if x and y are random variables with joint PDF, f sub x comma y of x comma y, then finding the marginal PDF or the PDF of single random variables for both x case and for both and for y case should be simple. If you recall, I told you that if you have a giant PDF, giant PMF of x comma y, you can obtain the distribution of x by simply summing the giant distribution and the variable missing here. So if you want to find the PMF of x, you take the giant PMF and sum it along y, the other variable. So here you have got giant PDF, so you integrate the giant PDF obviously on the meaningful range with respect to y. If you differentiate the giant PDF with respect to y, you obtain the PDF on the other variable, as we did in the case of joint PMFs and the marginal PMFs. And similarly here, if you have giant PDF available and you want to find the PDF of y, integrate the giant PDF on the variable other than y. So the other variable is simply x. So you differentiate it with respect to x. So this was a quick look at some of the a quick look at some of the basic concepts. The expectation of a continuous random variables, more than one continuous random variables, is also simple. I'll simply give you the formula and you should be able to understand the concept. So the next quick topic is giant expectations, or the expected values. Remember, I'll ask Mr. Zever, the other co-instructor in the course, to give you a few more examples on the topics that have been discussed here in this lecture. So what about the expected values, which means the giant expectations? which means if you have, say, some function, some random variable w, which is obtained by applying some functional form on the two random variables x and y. So if we have this random variable, the expected value of this random variable, which is nothing but a function of x and y both. So the expected value of w will be basically the integrals from minus infinity to plus infinity, the function, which is basically a function of two random variables, times the giant PDF times dx dy. So the formula is basically the same, except that now the single variable function is turned into a function of two random variables, and obviously then you'll utilize the giant PDF to find this expectation. Remember that particular theorem, this that we discussed in discrete case, that also uh, applies in continuous case, and that says for any two continuous random variables x and y, the expectation of the sum of two random variables is simply the sum of individual expectations. This was the famous function of two random variables that we deeply discussed in the discrete part of this course. The same applies here. Whether x and y are independent or not, this relation stays valid for both cases. And this also means that if you want to find the expectation of the sum, if you follow the usual formula, you'll have to utilize the giant PDF of the sum, and then you integrate and find the total expectation using that particular formula of expectation. But if you do not do this, you can still find the giant expectation and the expectation of the sum of x and y by simply adding up their individual expectations, the expectation of x plus the expectation of y. The other formulas stay the same. For example, the covariance will be the expectation of x minus the mean times y minus the mean. And the variance of the sum is given as this. Is variance of x plus variance of y plus 2 times covariance of x and y. And if you recall, this covariance of x was nothing but the expectation of x minus its mean times y minus its mean. So this is simple. The remaining formulas stay the same. So dear students, I'll now wrap up this lecture. So we started another chapter that is about multiple continuous random variables, and first we uh, tried to understand what we mean by giant CDF. Giant CDF means the uh, the small areas obtained by uh, using the intervals on x and intervals on y, and then their giant occurrences and the probability of their giant occurrences, and we keep on adding those probabilities, say arriving from minus infinity at y and minus infinity at x, and you simply keep on adding those probabilities, you get the giant CDF. And then we discuss these four important concepts. The giant CDF is obviously always between 0 and 1. It can never be below 0 and it can never be above 1. And if you are on minus infinity on any of the variables, then obviously there the giant uh, probability, the probability of giant occurrence will be 0 on some intervals, and so it is equal to 0. So if you move to minus infinity on x-axis or minus infinity on y-axis, the CDF will be 0 there. And if you have some higher points x1 and y1 which are higher than or greater than x and y, the giant CDF will obviously be more than the giant CDF or at x comma y. This is so obvious because the giant CDF philosophy is that you keep on adding the probabilities till that particular point. So at every higher point x1 comma y1, you have more probability, and CDF reaches 1, and then from there on, even if you move till infinity, the CDF remains 1. We did a simple example on the operating lives of two components. Operating lives are random variables x and y, and their giant CDF is supposedly given as this. We don't need to go into the details on how this is obtained. You just simply remember that this is given, and if that is given, we can find the probabilities, meaningful probabilities of our interest. Then we moved on to the concept of giant PDF, and we already know that a PDF for a continuous random variable can be obtained by differentiating the CDF. So for a giant case of two random variables, the giant CDF will be differentiated to obtain giant PDF. But since now there are two random variables involved, so we'll have partial derivatives. So if we use this particular formula, we can arrive at giant PDF of x and y from the giant CDF of x and y. And I gave you this theorem as a kind of warning, as a kind of pointer, as a kind of memory aid, that try not to utilize the expressions for CDF if you are handling more than one random variable simultaneously. For single random variable case, to find the probability, the meaningful probability, it is always recommended that you utilize the CDF expression because it gives you results in a quicker time. But for more than one random variable, for more than one continuous random variable case, it may take more time than the usual integration. The giant PDF has two properties, and these are related to the probability axioms. The giant PDF, the probability is 0 or above, and if you add up all this probability, ultimately it reaches 1. So the total probability cannot go beyond 1. Then we did some small example of uniform giant distribution and found two meaningful probabilities, and another example on how to obtain the giant PDF from a giant CDF. So you simply do the partial differentiation, and partial differentiation should be simple. You take the function, the giant function, and differentiate with respect to one of the variables, taking the other variable as constant, and in the second go you differentiate with respect to the other variable, assuming the first variable as constant. So this is the example, and this is the kind of homework that you differentiate this first with respect to y, keep x as constant, and then the resultant expression should be differentiated with respect to x, keeping y as constant, and you should be able to reach this particular expression. What about marginal distribution? Marginal distribution concept is simple. If you remember the concept of marginal distribution for discrete cases, you find the probability PMF of x from the giant PMF by summing up the giant PMF on y, the other variable other than this. So same is the case here. You simply integrate the giant PDF on the variable which is not here. So if you want to find the PDF on X, you differentiate the giant, sorry, you integrate the giant PDF with respect to Y. And if you want to find the PDF on Y, you differentiate with, you integrate on X. You see here it is summation, and here it is a continuous case, so you replace summation with integration, and you replace giant PMF with giant PDF. The expected values case is simple. The formula stay the same, the concept stays the same, except that now you will use integrals instead of summations, and you will use PDFs instead of summations. This important case of two random variables as a sum, it is a special case, and to find the expectation of the sum, you simply need to find the individual expectation, and that will be equal to the expectation of the sum. So you don't need to utilize even the giant PDF here. The variance case is repeated, and this is all about today's lecture. In the next lecture, we'll try to wind up this multiple continuous random variable case, so that we could move on to the last chapter, that is about stochastic processes. Thank you very much for your time. Mr. Zevar Ali, the other instructor in the course, will give you a few more homework problems to strengthen your concepts discussed in this particular lecture. Thank you.